Welcome. My name is Ellen Meyer, and this is a presentation that was given at the 2020 World Aquatic Health Conference on change requests that have been submitted for the Model Aquatic Health Code. After the Council for the Model Aquatic Health Code met, several change requests were changed and modified. So this presentation has been modified to reflect those new proposals. I hope this is useful to you as you try to navigate through the myriad of change requests for the MAC. My email is at the end of the presentation. If you have any questions about cyanuric acid, about the change request, the content of this presentation, please feel free to email me. Before I start, I would like to caution you to make sure that when you look at these different change requests, that you make sure that you're voting on the most current one. And for all of the change requests that were changed before the CMAC conference, the TRC form reflects the latest version of all the change requests. As I'm recording this, which is on Friday, November the 13th, voting opens today, so we wanted to go ahead and get this recording posted, but the TRC forms do not currently reflect the latest text that is in the change request. It's actually the change request form themselves that was changed, at least for the cyanuric acid change request that I'm going to be presenting to you today. So if you have any questions, please feel free to email me or any of the CMAC organizers, and we can make sure that you know exactly what it is that you're voting on. And hopefully all of the IET issues will be resolved so that it will be clear just from going onto the CMAC website what the actual text is that you will be voting on. Anyway, so let's go ahead and get on to the subject at hand, which is cyanuric acid. And I'm going to give a little bit of background information on cyanuric acid, talk about this chlorine stabilizer ad hoc committee that the CMAC organization pulled together, and then talk about the change requests themselves. And I've grouped them according to different groups. So minimum disinfection levels, maximum cyanuric acid, testing, training, form stool, and imminent health hazards. So first about cyanuric acid. One of the reasons why we would want to use it is that chlorine can be degraded by the UV rays of sunlight. And if you have cyanuric acid present in the water, then you can maintain a residual much more easily because it's protected from UV when it's bound to the cyanuric acid ring. So this is some old data from back in the 70s that Kennelly generated, where he saw that if he started out with 2.5 parts per million of chlorine, and after an hour of sunlight exposure, you can see about 80% of the chlorine was remaining if there was some cyanuric acid in the water, but only about 25% if there was no cyanuric acid. And you can see that it really doesn't take a lot of cyanuric acid to get that stabilization effect. So by about 20 parts per million of cyanuric acid, you have that full stabilization where you can maintain a residual. So this is what's going on from a chemical perspective. So you have your free chlorine in water is HOCl. The cyanuric acid ring is shown there, and that cyanuric acid ring can bind up to 3 chlorines. If it's binding 3 chlorines all at the same time, then that is a solid chlorine product that is sold for sanitizing pools, and that's called trichloroisocyanuric acid. And you can see there's a double-headed arrow there, and that shows that the reaction can go forwards and backwards. So the chlorine can go on the ring and then come back off again. So there's an equilibrium involved. In general, I'm going to be talking about isos, and isos are both trichlor and dichlor, so that cyanuric acid ring with 2 chlorines on it. Those are both chlorinating products that are sold into the market for sanitizing pools, and I'm going to talk about them as a group and calling them isos because they are isocyanurates. All right, so that equilibrium that we just showed is actually pretty complex because that cyanuric acid ring can bind hydrogens or bind chlorines. So up to 3 hydrogens, up to 3 chlorines. And so you get any kind of combination of all 3 chlorine, all 3 hydrogen, 2 chlorines, 1 hydrogen. And you can see all the different combinations that are on this sheet here. And there's equilibrium between each of them. And so it can be very complex trying to work out the chemistry of this, but it is possible. And O'Brien is one who took all of these equilibria and gave us numbers so that we can actually do those calculations to calculate how much of each of these species is present in the water. So on a simplified view, this is just the effect of pH on chlorine. So HOCl is our primary sanitizer in pools, and it will dissociate in water. So it'll split up into hydrogen ions and hypochlorite ions. Now the hypochlorite ion, the OCl minus there, that's a lot less effective at killing bacteria and viruses, and HOCl is much more effective. So we really want to make sure we have enough HOCl in the water. And you can see from this chart that as the pH increases, then the concentration of HOCl decreases. So within pool pHs of 7.2 to 7.8, about 50% of our chlorine is present as active chlorine, as HOCl. And you can see in the little table on the right, there's the actual numbers for what goes into the graph. So at pH 5, almost all of it, 99.7% is HOCl. pH 9.5, only about 1% is present as HOCl. And pH 7.5, about half of it is present as HOCl. So this is a graph showing you what happens with cyanuric acid present. So as I showed on the previous graph, if we have a pH of 7.5, then about half of our chlorine is present as HOCl. So you can see all of the lines there on the graph start at about 50%. And then as cyanuric acid concentrations increase, the HOCl concentration decreases. And you can see the lines for 1 part per million up to 10 parts per million. And you can see, just like with the graph that I showed you previously, that it's those first few parts per million of cyanuric acid that can make a big difference. So if you look at the table on the right, you can see that with no cyanuric acid present, about half of our chlorine is present as HOCl. But when we get up to 50 parts per million of cyanuric acid, if we have 1 part per million of free chlorine in the water, only about 1% of that is present as HOCl. This next graph shows both that Kennelly data that I showed you earlier and data for 2.5 parts per million of chlorine with increasing cyanuric acid. And you can see that these two graphs are not exactly mirror images of each other, but they're pretty close, showing that those first few parts per million of cyanuric acid have a really large effect, and then the effect levels out with higher concentrations. So you get a lot of diminishing returns. You don't get as much stabilization effect with increasing concentrations of cyanuric acid over 20 to 40 parts per million. So I've been talking about how HOCl is our primary sanitizer, but our committee wanted to confirm whether that was actually really true or not. So we looked at every data set that we could find in the literature, tried to estimate how much HOCl was present in those studies to see whether the disinfection was actually correlated better with HOCl or with the measured free chlorine. And the best data set that we had was from Jennifer Murphy from CDC, and this is the data that she generated for cryptosporidium. And she very graciously offered us her raw data so that we could have the really good data set in order to perform these calculations. And on the left, you can see that the CT on the x-axis is based on free chlorine for that first graph on the left. And then the log P over P is the log removal of, or log inactivation of the organisms of the crypto. And you can see that if you base your CTs on free chlorine, there's not very good correlation with just free chlorine. But over on the right, you can see the second graph that shows CTs based on HOCl. And you can see that there's much better correlation. And we pretty much saw that with all the different data sets that we looked at, where there was a much better correlation with HOCl than there was with free chlorine. So this definitely supports that HOCl is our primary sanitizer in pools, and it's that HOCl that we need to pay attention to make sure that we're disinfecting properly. One of the things you can do once you know that it's HOCl that you're looking at is just this kind of make an estimate of, okay, let's start adding cyanuric acid in, and how much longer is it going to take to kill my organism? So here's a theoretical organism that has a CT value of 1. So 1 part per million minute is enough to inactivate the organism. So if we have 1 part per million of free chlorine present and it takes 1 minute to kill it, what does that mean then when we start adding cyanuric acid into the water? So if you look at the table over on the right, you can see a cyanuric acid concentration of 0, about half of our chlorine is present as HOCl, and it's killing it within 1 minute. So now let's look at 10 parts per million of cyanuric acid. So with 10 parts per million of cyanuric acid, our HOCl is decreased down to 0.04. So you can see with that CT concept, if we have 1/10 of the sanitizer in the water, it's going to take about 10 times longer than to achieve that same amount of kill. And here it comes out to about 12 minutes. With 20 parts per million, about 24 minutes. With 50 parts per million, about 63 minutes. So just roughly, it's not exactly a 1-to-1 correlation, but approximately for every 10 parts per million of cyanuric acid, it's going to take about 10 times longer than to kill the organisms. So this is the same kind of graph, just showing a different CT value. So if you had a CT value of 45, you can see that with 10 parts per million, instead of taking 3/4 of an hour to kill the organism, it's going to take about 9 hours. With about 50 parts per million of cyanuric acid, it could take about 2 days, about 48 hours to kill the organism. So for an organism like Giardia that has a CT value of about 45, if you want to be able to kill it within 1 day, you need a ratio of cyanuric acid to free chlorine of about 20, 22 to 1 to make sure that you could actually kill Giardia within a day. So we know HOCl is our primary disinfecting species, but there's a problem because we don't have any test kits that directly measure HOCl. So how do we make sure that we have enough HOCl in the water? So before I address that question directly, we need to make sure we're all using the same language. And that's going to bring us to our first change request. Now, this is a DPD FC definition. So DPD is the typical test kit that we use for measuring chlorine residuals. And it measures chlorine that's bound to cyanuric acid as free chlorine. So even though that chlorine is not technically free because it's bound to the cyanuric acid ring, when you measure it with DPD, it appears as free chlorine. So the MAC defines free chlorine as just HOCl and OCl minus, not chlorine that's bound to cyanuric acid. So it's really important to distinguish between the chlorine that we're measuring with our test kits and the chlorine that the MAC is specifying as free available chlorine. And so that's why this definition is needed, to make sure that when we're talking about free chlorine, which kind of free chlorine are we talking about? Are we talking about the MAC definition for free chlorine, or are we talking about what's actually being measured with our DPD test kits? So this is just a slide to show you how this can be really important about how you actually define free available chlorine. The text that's in black at the top of the slide there is all direct quotes from the Model Aquatic Health Code, the 2018 version. So you can see free chlorine residual is just HOCl and OCl minus. And then if you look at section 5, where the operational requirements are, you can see that pools are required to maintain a free available chlorine concentration of 1 part per million. So this is not 1 part per million as measured with the DPD test kit. This is 1 part per million of HOCl and OCl minus. So you can see, already looking at this, right, I think a lot of us are probably not in compliant with the current Model Aquatic Health Code because of this definition. So we really need to make sure that we update this, that we put this definition in and make sure that everyone is clear about whether we're talking about truly free available chlorine, which is HOCl, or whether we're talking about that combination of chlorine that's bound to cyanuric acid and free chlorine that is DPD free chlorine. So just to kind of give you an idea, if we were actually going to try to achieve what the MAC currently says of getting 1 part per million of free available chlorine in the presence of 20 parts per million of cyanuric acid, then our DPD test kit reading would need to be over 10 parts per million. So we really need to make sure we get these definitions straightened out. All right, so now that we're all speaking the same language, let's talk about this thing called a ratio. So the Cyanuric Acid Committee has been looking at this issue and has done the calculations of how much HOCl that you have with various amounts of free chlorine and cyanuric acid. And it turns out that as long as you keep a ratio of cyanuric acid to DPD free chlorine constant, then you have a constant HOCl concentration. So I'm going to start by looking at the table on the right. So if you have a ratio of 10 to 1, of 10 parts per million of cyanuric acid for every 1 part of DPD free chlorine, then your HOCl concentration is 0.04. So if your cyanuric acid is 10 and your DPD is 1, it's 0.04. If your cyanuric acid is 20 and your DPD is 2, then your HOCl is 0.04. If your cyanuric acid is 100 and your DPD is 10, then your HOCl is 0.04. So as long as you keep that ratio constant of 10 to 1, then your HOCl concentration will be 0.04. The table on the left just shows the different ratio. So if your ratio is 20 to 1, then if you had 20 parts per million of cyanuric acid, 1 part per million of DPD free chlorine, your HOCl concentration is about 0.02. If you had 100 to 5, then it's still 0.02. That's where that ratio concept is coming from. We know our HOCl is our primary sanitizer. We need to make sure we maintain enough HOCl in the water. And so the way to do that is to look at our cyanuric acid reading and our DPD free chlorine reading, and then we can estimate then what our HOCl actually is. So what do we know so far? We know that HOCl is a primary disinfectant. We know that cyanuric acid lowers HOCl concentrations. So it's going to take longer to kill pathogens when that happens. We can't measure HOCl with pool test kits, but we can measure our DPD-free chlorine and our cyanuric acid levels so that we can estimate the HOCl concentration. So we can all agree up to the science up to this point. The science is very clear, but there's still a lot that we don't know. We don't know how much HOCl is actually enough. Now, this is a judgment call that we are still struggling with. Do we need enough to kill E. coli in 30 seconds, which is basically the EPA requirements for registration of a disinfectant for pools? Do we need enough to kill Giardia in a day or a week, or how long, what kind of time frame should you put on it? Do we need enough to meet the EPA drinking water standards? Or is it good enough to meet the EPA swimming beach standards? So the swimming beach would be untreated water. So there's all these questions about, how much disinfection is enough. And that's one of the reasons why we're having so many issues with all these change requests, is because it is very difficult to define that line in the sand. So because this has been an issue for quite a while, the CMAQ organization pulled together a committee that's called the CMAQ Chlorine Stabilizers Ad Hoc Committee. And I've referred to it a little bit already in this discussion. And we've been working together for quite a while now, for about 4 years. And we looked at all the data that we could find on cyanuric acid and then tried to pull it all together to try to figure out how can you draw that line in the sand to figure out what is good enough. And what we decided to do was to look at the risk. So what would actually be the risk of getting ill if you don't have sufficient disinfection? And to do that, we looked at whatever data we could find and tried to pick an assortment of organisms that would show really easy to kill organisms and really hard to kill organisms and something in between. So E. coli is very easy to kill with chlorine. Crypto is very hard to kill with chlorine. And Giardia was one that we chose that was just in the middle to give an idea then of how would organisms look then in these kinds of ranges. We just looked at ingestion. So we didn't try to simulate Legionella with inhalation or Pseudomonas with having rashes. We just looked at ingestion, and we just looked at routine fecal sloughing. So this would be the fecal material that would be adhering to people's backsides, not from an accidental fecal release. So we wanted to try to keep the whole, it's already complex enough, right? So, but we wanted to try to keep things as simple as we could so that the model would be clear and concise and that we could actually hopefully get some calculations that made some sense. So when we were trying to think about, okay, so here's our organisms, here's what we're going to try to model, then the question is, okay, well, where do we draw the line in the sand? And there's a number of different ways you can do it. If you look in some of the state codes, such as New Jersey, they actually have a limit for total coliforms of, less than 1 colony per 100 mils is the limit. The WHO also has, thermotolerant coliforms or E. coli less than 1. It needs to be less than 1 per 100 mils. But in the United States, there isn't a generally accepted national standard for what is the pathogen concentration that's acceptable in a swimming pool. So we have data for drinking water, but we do not have anything for swimming pools. And so our committee then decided to look at 2 different standards that are national standards. One is the EPA drinking water standard. So basically EPA in their standards, they set their limits to where the risk would be less than 1 per 10,000. So less than 1 person per 10,000 would get ill. EPA has also set standards for beaches. So these are untreated water like lakes. And that risk standard that they set is 36 per 1,000. And so this is based on surveys of people that actually came to beaches. And so if they're actually present, participating in beach activities, and that means that they accept that level of standard. And so they're saying that the level of acceptable risk then for beaches is 36 illnesses for every 1,000 people. All right. So this is a graph that was taken directly from the paper that we published. And I'm going to spend a couple minutes on it here. Along the x-axis, along the bottom there, you can see the cyanuric acid to free chlorine ratio. So with increasing ratios, you have more and more cyanuric acid, meaning you have less and less HOCl in the water. Along the y-axis, the vertical axis there, is the annual probability of infection. The top dashed gray line there is for the beach criteria for EPA. So this is the 36 per 1,000 people. And this is what is considered acceptable then for people who are going to a venue that has untreated water. The second gray line there that's at 10 to the minus 4, that's the level for EPA drinking water, so 1 per 10,000. And you can see the green line there for E. coli. Because E. coli is so easy to kill with chlorine, the risk of E. coli infection are very, very low and can even meet EPA drinking water standards using the assumptions that we put into our model. And you can see that for Giardia and crypto, on the other hand, even with no cyanuric acid in the water, if you're maintaining a chlorine residual, you still might not be meeting the EPA drinking water standard. And you can see that as the cyanuric acid concentration goes up and that ratio goes up, then the annual probability of infection also goes up with time. So you might be tempted to look at that black line, which represents Giardia, and see that it crosses that line for the beach standard, around 20 to 1. And in our committee, actually, when we wrote the paper, did recommend a ratio of 20 to 1. But I would definitely like to caution you on, the model itself. There's a lot of variation in the model. And so trying to find exactly where that line crosses the EPA beach line, it's very problematic. And I'd like to talk about that with the model limitations on this next slide. And the model is very good at predicting relative risk. So we calculated that the risk of E. coli infection increases 5-fold when the ratio is changed from 20 to 1 to 45 to 1. And the risk of Giardia infection doubles when the ratio is changed from 20 to 1 to 45 to 1. But the risk model is not good at predicting absolute risk with any certainty. There's a lot of input parameters that go into it, and a lot of these input parameters vary by orders of magnitude, meaning by more than an order of 10 or 100. And so with that kind of variability with the numbers going into the model, it's very hard then to have any absolute risk values that have any kind of certainty behind them. So here's a diagram from the paper that shows all the different components that go into the model. So I'll start over on the left there. So you have your pathogens getting into the water. Most of them are being contributed by your bathers. So bather load certainly is important in how much fecal material that they're contributing. And then you also have your chlorine chemistry then killing the pathogens. So pathogens going in, pathogens being killed, the relative rates, and so what's that concentration of pathogens that's actually in the water? And then the pathogens can move about in the water. So there's diffusivity within the water. And then those concentrations also depend on other pool parameters, such as the pool depth and then the distances between your bathers and the water. On the far right then is once your bathers actually swallow the water, then there's different variables about how much water they actually swallow, how many organisms does it actually take to make them ill. So there's a lot of different values that go into this model, and there's a lot of uncertainty in all these values. And as part of our process of developing the model, we did what's called a sensitivity analysis. And that was to look at all the different variables that we were using and all the numbers we were using to input into the model and looking at their effects on the final answer. So along the horizontal x-axis at the bottom there, you can see the log of max probability over min probability. So if the value is 4, this is log. So if it's 4, that means 10 to the 4 difference. So that would be the difference between 1 in 100 or 1 in a million. And so that can be a huge difference then in the actual risk. And if you look at the top of the chart, those are the ones that have the greatest variability. So the fecal introduction rate has a huge effect on the actual risk that's being calculated to 10 to the 4th differences between the minimum and maximum values that we chose to use in the model. The pathogen fecal concentration, so that's how many organisms are actually in the fecal matter that's being contributed to the water. Obviously, cyanuric acid has a big effect, particularly for E. coli, and the temperature, and then on down with other different variables, including distance between the bathers and secondary disinfection. So you can see that there's a lot of different values that go into the model, and so trying to come up with absolute values can be problematic because there's so much variability. So some of the change requests that have been submitted start tweaking some of these input values. And I just wanted to talk a little bit about some of those some of those values that have been talked about. One is lower bather density. The value that we chose to use in the paper was 15 square feet per bather, and that's the number that's in the Model Aquatic Health Code currently for agitated water. And it's been argued that the flat water value should be used, and that flat water value is 20 square feet per bather. So there have been, a lot of different discussions about which number is most appropriate. The worst case would be the 15 square feet per bather, and we, in general, tried to use worst case scenarios for the model. And certainly, there's a lot of pools that have been built with mushrooms and fountains and all kinds of things that would classify them as agitated water venues, and so we chose to use that value. For the pathogen removal with filtration, filtration is one that we considered adding in when the model was developed, and there is a way to actually estimate how the risk will change when you put filtration in, or UV disinfection or some other kind of secondary disinfection. We chose not to do that during the paper. One of the reasons is that the Model Aquatic Health Code does not recognize filtration as a means for removal of pathogens that you can get credit for it. At least that's the way it was for the 2018 MAC. And so we might possibly see some changes to that with these change requests that have been proposed recently. But at least as far as what was in the 2018 MAC, there weren't any ways to actually certify a filter for pathogen removal. NSF had just recently this fall voted on a change to NSF 50 so that filters can actually be listed and tested to ensure that they're removing some pathogens and then get listed for their removals. So that's coming, but we don't have that yet. And certainly when we wrote the paper, we didn't have that in place yet. Diurnal recovery while a pool is closed is an issue because obviously most pools are not open 24/7 and they're not at their really high bather load 24/7. And so there can be bathers in the water most of the day, and then at night, then the pool can recover. So this diurnal recovery can definitely make a big difference when your organisms are lasting that long. So if your organisms are still alive at the end of the day when the bathers go home, then that diurnal recovery can make a huge difference. Obviously, if you're killing your organisms within seconds, then that diurnal recovery isn't making much of a difference. But for the organisms like crypto or giardia, when you have a lot of cyanuric acid in the water, then the kill rate for those organisms can go into days, and therefore that diurnal recovery can become important. On this next slide, I'd like to show some of the factors that can show higher risk. So the ones I showed previously, if you choose to use filtration, diurnal recovery, that would indicate a lower risk, indicating that you could use a higher cyanuric acid. These are all values that would show a higher risk, meaning that you might want to control your cyanuric acid a little more carefully. And these are one that the equilibrium constants that we used in the original model are based on ones that were generated from O'Brien that I mentioned to you earlier from back in the 60s. And more recently, EPA, David Wamman, has generated new equilibrium constants. And so if you use the new updated constants, then it looks like the risk is actually a little higher than using the O'Brien constants. And so we might need to control our cyanuric acid a little lower than based on those results. The next line there is about the fecal introduction rates. There are various sources for how much fecal material might be contributed to pool water. The numbers that we chose to use were from Kooten. Kooten ran a study where he had a shower stall installed next to a pool where they collected all the water from the shower. And he had people with their swimwear on shower for 30 seconds. And then with that collected water, then they looked to see what kind of organisms were contributed to that water that was washed from their bodies. So as you can see, with the 30-second shower, you're obviously not going to be getting all of the organisms from the swimmers. And then since they're wearing their swimwear, any fecal material that's adhering to them is less likely to be washed off into the water with just the 30-second shower with their swimwear on. So those are not worst-case scenario values. They're more best-case scenario values. And there's some other studies. There's one from EPA where they took shower water from households, where you can assume that there was a more thorough cleansing with soap getting these organisms then off. And so the estimate from that is 72 milligrams per hour, whereas the Kooten values, we estimated 19 milligrams per hour fecal material being contributed. And then there's a study from Charles Gerba, where he was also looking at shower water, and those numbers were much higher. The values that he had, or that we calculated from his values, was 575 milligrams per hour that were being contributed. So you can see there's a broad range of fecal introduction rates, and it can make a big difference in the final values, which value you pick. There's also various sources available for the Giardia concentration that's in stools. The numbers that we used were from Danziger, and that's about 4 times 10 to the 5th per gram of stool. Feacham estimates somewhere between 10 to the 5th to 10 to the 7th, and Jakubowski had values that were about 1 times 10 to the 6th. So again, you can see that the Danziger value is on the low end rather than on the high end. And if these other numbers are used, then it would indicate that the risk would be higher than what the model is indicating. Another assumption that's used in the model is a water depth of 3 feet, which is a good average for most pools, but there's a lot more pools that are using beach entries. And with the beach entry, you have very, very shallow water. And so that can definitely increase your risk in that area. So if you have an organism like Giardia that's being mixed throughout the pool and it takes a lot of time to kill it, it won't make as big of a difference. But for something like E. coli, where you're counting on that E. coli being killed within seconds, that very localized area around the person who is contributing the E. coli to the water can make a big difference. Anyway, so the assumption in the model is to use 3 feet, but if you use, a beach entry kind of scenario, then the risk is certainly higher, particularly for something like E. coli. Another thing that we didn't even try to do in the model was to account for non-instantaneous replacement of the chlorine. So we know that if you have a chlorine residual in the water, and then a swim class gets in, that chlorine residual is going to decrease because of all the bather chlorine demand that's being contributed to the water. In the model, it would have been very difficult to try to incorporate that timing into the model. So we just assume that any chlorine that's used up is instantaneously replaced. So we know that's not actually true in a pool, but to make the math easier, that was the assumption that we made. And so obviously, if we don't have instantaneous replacement of our chlorine, then that's going to increase the risk. So this slide here shows some values that were taken from one of the change requests where they're talking about using different values for input. So if you look at the green line along the top, the Falk 2019 paper is the paper that our committee published, and with all the default values that are used within the paper, you can see that the ratio to reach that beach standard of 36 per 1,000 people getting ill, that ratio comes out to be 22 to 1. The change request argued that, okay, well, let's use 20 square feet per bather instead of 15 square feet per bather. And if we do that, then the ratio goes up to 30 to 1. Then it said, well, okay, what about filtration? If we assume that we get 30% removal of Giardia from the pool with filtration, and then add that in then to the 20 square feet per bather, then the ratio goes up to 39 to 1, excuse me. And then if you add diurnal recovery, so the pool is open for 12 hours, pool is closed for 12 hours, add in the different bather load, add in the filtration, and then the ratio comes out to be 45 to 1. So those are all from that change request. And those are highlighted in blue there. Then if you look at the yellow line, this is if you look at a different fecal introduction rate. So instead of using the Kooten value of 19 milligrams per hour, let's just look at the EPA value of 72 milligrams per hour. And that includes both, oh, I forgot to mention that the Kooten value is just adults, whereas the EPA data includes adults and children. So if we use that number from EPA that includes kids, then the ratio that's calculated of where it crosses that line for EPA beach criteria is 7 to 1. So you can see it's much, much lower ratios based on that different fecal introduction rate from EPA. So if you want to kind of see, well, okay, so we have some that are bringing the ratio up, we have another one that's bringing the ratio down. What do we do when we combine it all together? So if we take everything in the blue and the yellow and combine all those different factors and put them into the model, the ratio that results is 9:1. So you can see this number still is much lower than the value that was in the original paper. The original default values of 20 that resulted in 22:1. So that ratio of 9:1 shows that that fecal introduction rate really dominates the statistics and really dominates what's going on with the risk that's involved here. So obviously, if all those other parameters that I had just shown you on the previous slide, if we had included those in these calculations, then the ratio obviously would be a lot lower than 9:1. All right, so this is my last slide before I actually launch into the change request. And this is just to show you what are the current Model Aquatic Health Code provisions. So the Model Aquatic Health Code currently requires that if you have no cyanuric acid in the water, you need a minimum of 1 part per million of free available chlorine. If you have any amount of cyanuric acid in the water, the minimum is 2 parts per million. The maximum cyanuric acid concentration that's allowed is 90 parts per million. And in the very last part of the MAC, where it has the reasons for immediate correction or closure, where if you exceed any of these, then you need to get all your bathers out and close the pool until things are corrected. And then you can let the bathers back in. And those are based on A and B, so the free available chlorine concentration. The cyanuric acid concentration does not currently appear in the reasons for immediate correction or closure. And just to point out, because we've been talking about ratios, that 90 parts per million with 2 parts per million of free available chlorine when cyanuric acid is present, that 90:2 ratio is an implicit 45:1 ratio. All right, so here's a bunch of change requests that talk about the minimum chlorine that's allowed in pools. As you can see, some of these are highlighted in red, and the ones that are highlighted in red are the ones that have been changed since the CMAC meeting. So just in the past week or so, these change requests have been changed. And so that's why I'm re-recording this webinar so that we can incorporate the changes. And so the change request that will actually be up for vote, and the voting opens today, is to make sure that you have the most up-to-date information. So let's talk about each of them. One is to change the minimum DPD-free chlorine concentration to 1 part per million for all pools. So currently, if you have any cyanuric acid in the water, you have to have a minimum of 2 parts per million. And this is saying, no, let's just get rid of that. Let's just require 1 part per million for all pools, regardless of whether they have cyanuric acid or not. The arguments in favor of this are that 1 part per million should be sufficient for pools with or without cyanuric acid, according to the calculations in the Falk model. As we talked about already, in the Falk model, there's a lot of variability, and so trying to make an absolute risk estimate that 1 part per million is sufficient, that's really hard to do given the variability in the models of the Falk model. Variability, excuse me. The second argument in favor is that a lot of European standards actually have less than 1 part per million DPD-free chlorine. However, a lot of the European standards, such as the DIN standard, which is used in Germany, don't allow the use of cyanuric acid. So that's a complicating factor there. And then the third reason was that 1 part per million of free chlorine in the MAC is not really the level required for disinfection, but it's the level required to meet the chlorine demand fluctuations. And the argument against that is that nowhere in the MAC, the code or the annex, does it indicate that 1 part per million of free chlorine without cyanuric acid or 2 parts per million with cyanuric acid are merely the means of maintaining some lower undefined minimum chlorine residual. The MAC states these values are the minimum chlorine residuals that must be maintained, not that they're a means of maintaining disinfection, but they are the minimums that are required. And the MAC does say that you can do things like, right, if you want to make sure that you maintain a residual of 1 part per million, you can have your residual at 3, you can have it at 4, you can have your residual at higher values to make sure that you never go below 1. It also says that you need to maintain your chlorine or have your chlorine feeders sized appropriate so that you can maintain that 1 part per million minimum. So it's clear that that 1 part per million minimum is for disinfection, not just as a means of meeting some other undefined minimum residual. And then just to point out, this is the last bullet on this slide there, marked D, and that's that the ratio CRs I'm going to be talking about, the 45:1, the 30:1, the 15:1, they also change the minimum DPD-free chlorine to 1 part per million for all pools, but that's as long as the ratio is maintained. So that's keeping then the cyanuric acid increase, or keeping the DPD-free chlorine increasing as the cyanuric acid concentration increases with those ratios. To make this change by itself without also having a ratio associated with it doesn't make sense. All right, so this next slide is about the 45:1 ratio. So this is cyanuric acid to DPD-free chlorine. And I showed you these numbers before, right? So if we take the different bather loads, if we take filtration, if we take diurnal recovery, you can see if we take those all three combined, then the ratio comes out then to be 45:1 when we're comparing our risk to the EPA beach criteria for Giardia. There's another one I haven't talked about here yet, and that's the one marked D. And that argument in the change request is about infectivity. So not every organism that you might swallow it has the capability of actually making you sick. And there's a lot of really good data that's referenced in the arguments for this change request about how, probably really only about 50% of those Giardia are actually going to be infective. But the problem with this is, with the change request, is that you can't assume that you have 50% infectivity for Giardia in the feces, but 100% infectivity for the dose response. So that dose response is, what is the dose of Giardia that would actually make you ill? And so for the Giardia going in the water, you can't assume 50% infectivity, but 100% infectivity for the bather swallowing the water. You have to do one or the other. But if you decide to do it anyway and do the calculations, then you can see the ratio goes way up to 235:1. The change request does recognize the Wamman constants from EPA, and so if you use all of those different values that are listed there on the slide, you can see that the ratio ends up at being 150:1. So the change request is not actually requesting a change to 150:1, but just a more reasonable 45:1. And on all of the ratio slides, up on the far right, in the upper right, there's like a little decoder. So the change request says that your DPD-free chlorine concentration needs to be greater than 0.022 times your cyanuric acid concentration. Another way to say this is that your DPD-free chlorine concentration needs to be greater than your cyanuric acid divided by 45. And the little table there just kind of shows you what that actually look like. So if you have 45 parts per million of cyanuric acid, you need to have at least 1 part per million of DPD-free chlorine. If you have 90 parts per million of cyanuric acid, you need to have at least 2 parts per million of free chlorine. If you have 135 parts per million of cyanuric acid, you need at least 3 parts per million of free chlorine. So I'm not going to go through each of those for each of these other slides in the interest of time, but just kind of wanted to show you how that works. So what are the arguments in favor of this? The arguments in favor are that 45:1 ratio is already implicit in the MAC with the current limits of 1 part per million or 2 parts per million of free chlorine with 90 parts per million of cyanuric acid. So that's already currently implicitly set as a limit within the Model Aquatic Health Code. It's been argued that no major changes should be made until absolute values can be calculated with the model. However, as we talked about already, there's going to be a lot of variability in the model no matter what. There's a lot of variation in microbe and human behavior that spans orders of magnitude. And so I don't think it's realistic to think that we will have absolute values from the model, certainly not within my lifetime. It's also been argued that we don't have any outbreak records that have attributed illness to cyanuric acid, so why would we even need to change anything regarding cyanuric acid limits? Most of the outbreaks are attributed to either crypto or less than 1 part per million of DPD-free chlorine. An issue with this, though, is that cyanuric acid is rarely measured in outbreaks, so we really don't know if it could have contributed to any of the outbreaks where the chlorine was greater than 0 but less than 1. We just don't know because we don't have the data. Another argument in favor of this change request is that it doesn't have any significant adverse impact on cost because it's not really changing much of anything. One of the other arguments against it is it may be difficult for operators and inspectors to get used to this whole ratio concept. And this is an argument against all of the ratio change requests, is that, sometimes it's kind of hard to wrap your head around exactly what the requirements are, and to educate everyone so that everybody's familiar and comfortable with working with ratios. Will definitely be something that we would need to put some effort into education. So I'd like to talk, go back to a couple of the issues on this, and one is about outbreaks, and the other one is a point here. You can see the arguments against for A, that the overall increase in risk. So just to let you know, that's coming up on an upcoming slide, but I'm going to look at outbreaks first, and then we'll go back to that overall increase in risk with this ratio. So on this next slide is data that we've all seen. These are the outbreak summaries that CDC puts out, and this is the data for 2013 to 2014, but it's pretty much true for all of the different outbreak summaries that crypto dominates. Crypto is the primary reason for outbreaks, and that's been true for years. And crypto is very chlorine tolerant, and so it's very hard to kill crypto with chlorine. And so then if you look at the other ones that are more likely to be killed with chlorine, then the chances of an actual outbreak are much, much, much lower. So this would indicate that, okay, well, maybe the disinfection that we have now is good enough, because we're not seeing a lot of Giardia outbreaks. We're not seeing a lot of E. coli outbreaks. But I would like to point out some other data from CDC. And this was from a study where they looked at emergency department visits. And there were about 500,000 emergency department visits annually that were due to 13 diseases that are caused by water pathogens. So of these, most of them actually, about 376,000 were treat and release, so that people were able to go home at the end of the day. And 97% of these treat and release cases were due to acute otitis externa, otherwise known as swimmer's ear. And they estimated that the cost was about $178 million per year due to these visits. So on this next slide, I want to show you just graphically how that looks. So you can see acute otitis externa, i.e. swimmer's ear, really dominates, kind of like crypto did, for these emergency department visits. And E. coli and Giardia and crypto are just tiny little slivers then on this graph. So there's a lot of limitations to this data. Whether it's E. coli, Giardia, or swimmer's ear, these are all the emergency department visits. So the E. coli could have been from food poisoning. The swimmer's ear doesn't necessarily need to have come from swimming in a pool. Just a lot of people, when you get an earache, they call it swimmer's ear. So obviously these data are not targeted towards just pool use and what happens in pools. So we don't know if the relative proportions are the same. Like if we were just to take pool incidents, would we still see these same proportions? But even if only a small fraction of the ear infections are actually due to swimming, I think it still shows that the ear infections would far outweigh the outbreaks that we've seen for E. coli and Giardia and crypto. And this next slide, you might be wondering, okay, well, ear infection, it's not that big of a deal. Whereas if you get really ill from something like E. coli or Giardia, like E. coli, particularly the 0157, could be deadly. You might think, ear infections are not that bad, but actually quite a few of these emergency visits actually resulted in immediate hospitalizations. So you can see that the swimmer's ear doesn't dominate the graph like it did on that other one, but it still is a much larger wedge than the ones from E. coli, crypto, and Giardia. So, these statistics don't tell us everything we need to know, and they don't prove that we need to improve disinfection in swimming pools, but they do indicate that the outbreak statistics might not be showing us everything that we need to know. I'd like to argue that, in the interest of public health, it might be a good idea to reduce the risk of infection rather than increasing it. So let's talk about risk. I told you I was going to return to that. And this is a graph showing what the different risks are for things that are currently in the MAC and for what's being proposed here. So I'm going to start with the first line that's in green there that says no cyanuric acid. So the MAC allows anywhere between 1 and 10 parts per million of free chlorine. So with 1 part per million of free chlorine, the risk is about 1 in 10,000 or so. And then with more chlorine, then the risk goes down. The MAC allows the use of cyanuric acid if you have at least 2 parts per million of free chlorine, and the limit is 90 parts per million. So if you have 2 parts per million of free chlorine, 90 parts per million of cyanuric acid, you can see that the risk is much higher. The risk is more like 1 in 1,000, 1.3 in 1,000, rather than 1 in 10,000. And then as you raise your chlorine concentration, cyanuric acid concentrations can't be increased beyond 90. So you can see that as you raise your chlorine concentration, then the risk is going to go down. So that's what's currently allowed in the MAC. So let's look at that 45-to-1 ratio. With the 45-to-1 ratio, as your cyanuric acid concentration increases, then your DPD-free chlorine is increased as well, as long as you maintain that 45-to-1 ratio. And so that's why that risk line is straight across, because the risk is going to be the same whether you have 1 part per million of free chlorine and 45 parts per million of cyanuric acid, or 2 parts per million of free chlorine and 90 parts per million of cyanuric acid. The risk will be the same because you have the same amount of HOCl in the water. So you can see that, with the current Model Aquatic Health Code, anybody can operate anywhere below that green line, right, with no cyanuric acid. Anybody can operate below that blue line if cyanuric acid is present. And so if you go with the orange line then, with the 45-to-1 ratio, you can see you have a much broader range of possibilities and a higher risk overall with that 45-to-1 ratio compared to what's currently in the Model Aquatic Health Code. Particularly if you look at the low concentrations. If you have 1 part per million of free chlorine, before you couldn't use any amount of cyanuric acid with just that small amount of chlorine in the water, but now with 45 parts per million of cyanuric acid present with 1 part per million, that risk is much higher than what's currently allowed in the Model Aquatic Health Code. All right, so let's go on to our next change request. This one is for a 30-to-1 ratio. This is the change request that was submitted by our committee. Our committee, when we wrote the paper, originally recommended a 20-to-1 ratio, and then that was eventually, after much debate, changed to a 30-to-1 ratio. Arguments in favor of it: it's lower risk than the 45-to-1 ratio. It is a result of the Cyanuric Acid Ad Hoc Committee compromise. So there's been a lot of input from both sides of the issue, of people who would like to lower cyanuric acid levels and people who would like to raise cyanuric acid levels. There's an argument that we don't need to wait until the model can calculate absolute values, because there's always going to be a lot of variability. And there's the argument also that it won't be a significant increase in cost. So pools that are running with 1 part per million free chlorine, now they can use cyanuric acid. So that would actually be a cost decrease. Pools with a minimum of 2 parts per million would need to drain more often. Arguments against it are that there is increased risk for some scenarios, which I'll show you a similar graph than the one I just showed you in just a second. There's a question about whether we really need to reduce the risk. About, we don't have any outbreaks that we know are due to cyanuric acid, so do we really need to decrease any of the risk? There's a question about just to mention, when I was preparing these slides, I looked at both the change request and the arguments for it, and I also looked at the comments that had been submitted about the change request to include any of their arguments about them. And one of the comments that was submitted about this one was questioning whether HOCl chemistry and efficacy are the same in field conditions. So, we have plenty of lab data showing that, yes, you have less HOCl in the water with cyanuric acid, and that kill times are going to be much longer when you have cyanuric acid in the water. But there's a question of, well, do you really have that happen in the field? And the argument against that is that, well, yes, the same chemical principles are working in the field as well as in the lab. Is the field much more complicated? Absolutely. So is it much harder to prove things when you have all these other variables in the water? Yes, it's much harder. But the same basic chemical principles are true whether it's in a beaker or whether it's in a pool. All right, there's another comment about whether the priority should not be on cyanuric acid, but on maintaining a residual, using secondary disinfection, operator training, and more frequent testing. And all of these absolutely are good things that we need to work on as an industry. I also think that we need to work on cyanuric acid levels. So yes, they're all things that we need to pay attention to. There's also the question of whether we just need to wait. the model could be improved, certainly, but we will never get to the point where you get absolute numbers from the model. There's also the question of whether we want to wait. Currently, EPA is evaluating the chlorinated isocyanurates. So EPA registers all pesticides, and chlorinated isocyanurates, because they kill things in pools, are considered pesticides by EPA. And on a regular basis, they review the registrations and review all of their assumptions and try to decide if they want to change anything. And EPA is currently doing that review now for the isocyanurates. So the question was, well, do we want to wait until we hear from EPA? And I would argue that no, we should go ahead and make changes that we know are good for public health. All right, so here's the chart that I showed you earlier with the 45-to-1 ratio, except this one shows what happens with the 30-to-1 ratio. So you can see that even just like the other one, with the 1 part per million of free chlorine, your risk is going to be higher because it's allowing some cyanuric acid to be present when you have just 1 part per million of chlorine. But you can see that that line is lower than the line for the 45-to-1 ratio. All right, the last ratio I'd like to talk about is the 15-to-1 ratio. The arguments in favor of this are it's obviously lower risk than a 30-to-1 ratio. And this one actually has a different way of drawing the line in the sand. So if you have greater than a 15-to-1 ratio, then the kill times for Giardia are calculated to be longer than 1 part per million of monochloramine. So we've been taught for years, right, that we don't want to sanitize a pool with combined chlorine. We want to sanitize a pool with free chlorine. And if we have a ratio greater than 15-to-1, then our chlorine really isn't any better than 1 part per million of monochloramine. So the arguments against this are that, questioning whether 1 part per million of monochloramine is an appropriate benchmark. Monochloramine has not been registered for pool use, so we really don't know what EPA would say would be the dosage that would be required to register it for pools. But we do know what the criteria are for registration with EPA, and essentially you need to be equivalent to chlorine. And so monochloramine obviously is not, and so you would have to have dosages higher than what is used for free chlorine. So we would obviously need a dosage higher than 1 part per million of monochloramine. So if 1 part per million of monochloramine isn't sufficient to be registered as a disinfectant for pools, why would we want to sacrifice our chlorine concentration to where with cyanuric acid so that it wouldn't be as effective as something that we know is not going to be good enough? So those are the arguments for it and against it. And then, of course, potential cost impact. So the lower the ratio, then if you're using ISOs to sanitize your pool, you will need to drain more often, and that will cost money. And so that should not be ignored, that there will be a cost impact. So this next slide shows all 3 ratios, just to compare all 3 of them so you can kind of see how they look relative to what's currently in the Model Aquatic Health Code. For all of them, for the 1 part per million free chlorine dosage is going to be higher risk than what's currently in the Model Aquatic Health Code, but then it's a flat line across, 45-to-1 highest risk, then 30-to-1, and the 15-to-1 has the lowest risk. So let's turn back to economic impact. There's a report from PK Data for 2017 showing that 85 to 95% of commercial pools don't use stabilized sanitizers. That means about 10% of the commercial pools out there use stabilized sanitizers. Most of these pools are most prevalently in the small commercial pool market, so hotel, motel, apartment complexes, which also happen to be where we have most of our outbreaks, is at these facilities. So trichlor, one of the reasons why it's most prevalent in these small commercial pools is that it's limited by its feeder size. The MAC does require that all chlorine feeders be NSF certified. And so I went on to the NSF listing site to see, okay, well, what's the biggest trichlor feeder that's out there that's NSF listed? And it turns out that the biggest one I could find was 7.68 pounds per day. So if you want to kind of figure out, well, how big of a pool can that treat? If you go back to the 2016 MAC, there's actually some values that show what the feeder sizing should be, and that's in pounds of free chlorine per day per 10,000 gallons. So in the 2016 MAC, it says for an outdoor pool, you need a feeder that can feed up to 4 pounds of free chlorine per day per 10,000 gallons. So if your feeder can feed 7.68 pounds per day, that means that your chlorine feeder would be sized for about a 20,000 gallon pool. Then for indoor, you don't need quite as much chlorine, and so the feeder sizing then would be for about a 30,000 gallon pool. So 20 to 30,000 gallons, these are small pools. These are more residential sized pools. And so you can see that the trichlor is limited, not only because it's slow dissolving and it doesn't respond quickly to chlorine demand, but the feeders just aren't big enough for large facilities. There's also an additional factor that cyanuric acid interferes with ORP controllers, and so it's difficult then for commercial pools to use trichlor for a number of different reasons. So for the overall impact of changing cyanuric acid levels, it's easy for a pool that's feeding cyanuric acid separately from their sanitizer. So if you're using chlorine glass or bleach or calcium hypochlorite, it's easy to feed your chlorine separate from your cyanuric acid, and so it's easy to maintain whatever ratio you pick, whether it's 15 to 1 or 50 to 1 or 45 to 1 or whatever. It's easy to maintain a ratio because you're feeding your sanitizer separately from your cyanuric acid. With trichlor, because every time you add trichlor to the water, it's also contributing cyanuric acid to the water, then it's harder to stay in control. But then only a small portion of low volume pools would actually be affected by this economic impact if we change anything with the cyanuric acid provisions in the Model Aquatic Health Code. So here's some numbers. Assuming a maximum DPD-free chlorine concentration of 4 parts per million, because that's the maximum that we have from EPA. I use the 15 to 1 ratio here because that's the most stringent one from all the ratios that are presented or that are currently in the change request for the MAC. And so if you have a 4 part per million free chlorine concentration and a 15 to 1 ratio, that means that you would be limiting your cyanuric acid to 60 parts per million. So if you look at 60 parts per million versus 90 parts per million, how much more water would you need to drain in order to maintain 60 instead of 90? And so there's a spreadsheet that Richard Falk developed for our committee to help do these calculations, and it shows that the amount of draining you would need to do would be 1.7 times what you would need to do with 90 parts per million. So there would be additional draining that would need to be done. So, you know, if you're in a drought area, you might need to look at other approaches, possibly look at other sanitizers or precipitation of the cyanuric acid with melamine. There's some new data from Rudy Stankiewicz. He's seen some good removals of cyanuric acid with alum. There's other folks who have said, well, it might just be a test interference, but it might, you know, if you're having issues, it might be worth trying that alum treatment to see whether it works. And of course, you could prevent, cyanuric acid levels climbing by just using an unstabilized sanitizer. All right, this next change request is one of the new ones. So this was not on the books at all during the previous or before the CMAC conference. And John Kelly submitted this after listening to all the different arguments about the different change requests and has proposed the following. Rather than lowering or rather than allowing cyanuric acid use for pools that just have 1 part per million, his change request is keeping that. So keeping it to where if you have cyanuric acid in the water, your minimum is going to be 2 parts per million of free chlorine. And then above that, he's using this little table. So the table there on the slide shows the first 2 columns are directly from the change request, and then the last 2 columns are what I calculated. So that if you have a minimum DPD-free chlorine of 2 parts per million, then your range of cyanuric acid that's allowed is anywhere between 1 and 30 parts per million. If you have if you have over 30 parts per million of cyanuric acid, though, you need at least 3 parts per million of DPD-free chlorine. And if your cyanuric acid is over 61 or over, then you need to have at least 4 parts per million of DPD-free chlorine. So if you want to think in terms of a ratio, what does this mean? So 2 to 30 would be essentially a 15 to 1 ratio, 3 to 60 would be essentially a 20 to 1 ratio, and 4 to 90 would be essentially a 22.5 to 1 ratio. And so the minimum HOCl levels that this represents then would be 0.027, 0.02, and 0.018. So that's what this new change request is saying, is that, okay, let's still, you know, any amount of cyanuric acid, we still need at least 2 parts per million of DPD-free chlorine. And then as the cyanuric acid rises, then we also need to increase our minimum DPD-free chlorine concentration. So just like the slide that I showed you before, I added in a line for this new change request, and that's the pink line here. And so you can see that it's right on top of the 15:1 ratio line at 2 parts per million, because like we said, it's about a 15:1 ratio. When you have 30 parts per million of cyanuric acid and 2 parts per million of free chlorine, it goes up a little bit to a ratio of 20:1, and then it goes on down because the cyanuric acid is still limited at 90 parts per million. All right, so the arguments in favor of this are that it prevents an increase in the risk compared to the other ratio CRs, like we saw on the slide we just showed you. And it does decrease the risk compared to what's currently in the Model Aquatic Health Code. It's consistent with the current Model Aquatic Health Code limits of 1 part per million of free chlorine with no cyanuric acid, 2 parts per million of free chlorine when you have cyanuric acid present, and the 90 part per million maximum cyanuric acid level. 30 parts per million cyanuric acid is sufficient to stabilize residuals, and so it's consistent with what would be needed to operate a pool. This change request was also submitted to represent evolution rather than revolution, and it made a comment about, until the ad hoc committee membership includes significant public health involvement, that potentially, different recommendations might have come out of our committee if there had been more public health folks on that committee. The table is meant to ease operation and enforcement with clear ranges that more easy to understand than the ratio concept tables that were submitted. And then also, as far as that there would be minimal change for pools using unstabilized sanitizers, and that for 10% of the pools that use stabilized sanitizers, these small pools can more easily drain to reduce cyanuric acid. Arguments against this are that it doesn't have a consistent ratio or consistent risk like the ratios change request, where that line goes straight across. And then, of course, there would be increased costs for pools with high cyanuric acid, since they will either need to maintain higher free chlorine levels or they'll need to drain to reduce their cyanuric acid. All right, next I'd like to talk about maximum cyanuric acid change requests. There's a number of different change requests that have absolute limits for cyanuric acid rather than going on that ratio concept, and just want to cover each of those. One is that cyanuric acid should be banned in indoor pools. Cyanuric acid isn't needed to maintain a residual in indoor pools. There's more risk if you have cyanuric acid present, and eliminating cyanuric acid then reduce the risk of disease transmission in indoor pools. Arguments against it are that if we can allow a certain amount of risk for outdoor pools, why can't we allow that same amount of risk for an indoor pool? So that would be a risk analysis. But if you look at the risk-benefit analysis, there's really no benefit to using cyanuric acid in an indoor pool. And so therefore, if you look at the total risk-benefit, it makes sense to ban it in indoor pools. There would be potential cost impact for switching sanitizers. It would be limiting options for pool owners. So rather than allowing them to use stabilized sanitizers, they would be limited to unstabilized sanitizers. There's also some data out there indicating that you might have fewer disinfection byproducts with cyanuric acid present because you have lower HOCl concentrations. So there's certainly some more research that's needed in this area. It's still very, very new, and so that certainly needs more research, but for now we can't really say for certain that running a pool will result in fewer disinfection byproducts with cyanuric acid present when you have the same disinfection ability with your sanitizer. The last argument against it is that, okay, well, some indoor pools do have some UV coming in from the windows, and so it might help then to have some cyanuric acid to help stabilize the chlorine because of that. Vertical windows don't really have a lot of UV because there's not a lot of direct sunlight then getting into the pool, but certainly if you have a roof made of glass, you would get a lot more direct sunlight coming through the glass. There's also windows that have UV blockers, so there's certainly other ways to get around it, but that is a consideration as far as banning cyanuric acid in indoor pools. All right, this next change request is about allowing cyanuric acid in spas and therapy pools. So currently the MAC does not allow cyanuric acid use in spas and therapy pools, and this is arguing that they should. It would provide more tools for the operators the ISOs are EPA registered for use in spas and therapy pools, so EPA doesn't see a reason for not allowing them use in those venues. And then I took a direct quote from the change request itself, saying that it has a long track record of successful and safe use. The arguments against it, I just took a direct quote, this time from the MAC Annex, pointing out that for spas and therapy pools, there's issue with efficacy in these systems because of biofilm, for one, particularly in spas where you have the high temperatures. It can easily promote growth of pathogens if you don't have sufficient sanitizer. And then once you have a biofilm, it's much harder to kill it. And so spas are already very challenged already. And so rather than trying to add to that challenge, just make sure that your chlorine is fully effective by not having any cyanuric acid in the water. Also in spas, your pH can drift up very easily. And so again, making it more of a challenge for your chlorine to work. And then for therapy pools and for spas as well, but mostly for therapy pools, you have an increased risk of people that are in the water. So the people have maybe compromised immune systems or wounds or whatever that would make them at increased risk of infection and potentially worse infections if they catch something. So for all those reasons, then the Model Aquatic Health Code currently does not allow cyanuric acid in spas and therapy pools. This next change request is a new one. It was again from John Kelly after listening to all the different discussions during the CMAC conference. And basically the change request is still to keep that 90 part per million cyanuric acid limit. But to add in some text saying that, okay, if you exceed the 90 parts per million, it's not necessarily a reason for immediate correction or closure where you have to get all your bathers out and fix it before the bathers can get back in. But you really should address it really soon. And so the thing is if it gets over 90, then that night, once the pool closes down, then you address it and then reopen it after you've gotten your cyanuric acid down to 75 parts per million. Then if your facility is a 24/7 operation, so you never actually close down, then at least make sure that your cyanuric acid gets down to 70 parts per million within the next 24 hours. So the arguments in favor of this are that it's consistent with the current 90 part per million cyanuric acid maximum. It's consistent with the recent work showing that HOCl really makes a difference as far as disinfection is concerned, and cyanuric acid lowers your HOCl concentration. It is evolutionary because it's helping with the enforcement without actually changing the limit itself. So it's not actually a change to that 90 part per million limit. It ensures that that HOCl disinfectant concentrations don't go below the operational limit. So it does make sure that actions are taken if you exceed 90 parts per million. And you might be wondering, well, where did that 75 parts per million number come from? Although the math isn't exact, if you have a 5 part per million per day chlorine demand, if you're using trichlor to fill that demand, then that would mean that you're having an increase in cyanuric acid of 21 parts per million per week if you're using trichlor. And that's not accounting for backwashing or drag out or other ways to reduce cyanuric acid, but that's how much cyanuric acid would be added to the pool with the trichlor that you're using. And so, 75 parts per million is kind of more of a round number. So that if you're testing weekly, then you should be able to stay on top of things and make sure you don't exceed 90 again. And then this value is consistent with the current NSF listed test kits that have a maximum of 110 parts per million of cyanuric acid. And we'll talk more about test kits on one of the other change requests we'll be talking about soon. Arguments against this are that it would increase water replacement if you're using ISOs, because currently you're not required to close or actually, drain anything, even though the limit is at 90. And then there's a question of whether 90 parts per million is an imminent health hazard and whether you need to, whether you actually need to reduce it or not. All right, this next change request is to limit cyanuric acid to 40 parts per million. So the committee that I mentioned to you already had published a paper, and in the paper, the ratio that was recommended was 20:1. So with the 20:1 ratio and with a 2 part per million minimum DPD-free chlorine concentration, then that would result in a 40 part per million maximum cyanuric acid concentration, if you want to be able to have 2 part per million as your minimum. And so, one of the arguments about the whole ratio is that people might have an issue with the ratio concept and just trying to get their heads around it. And so rather than setting a ratio, why not just limit cyanuric acid? And so using that 20-to-1 ratio and the current minimum DPD-free chlorine, then that comes out to be 40 parts per million of cyanuric acid. The arguments against it are that it would obviously increase the water replacement cost if you're using ISOs, and it doesn't use the ratio concept. And then there's the question of whether you need to reduce the risk or not. There's another change request saying that, okay, well, instead of using our minimum of 2 parts per million of DPD-free chlorine, what about raising it to 3 and then setting our maximum to 60 parts per million of cyanuric acid? So that's just, again, based on that 20-to-1 ratio from the paper that was published by our committee. Arguments against it are the same. Increased water replacement costs, doesn't use the ratio concept, and then the question whether we need to reduce the risk or not. This next change request is to actually raise the level of cyanuric acid limit. The arguments in favor of this, is to raise it to 180 parts per million if you're able to test it. So I didn't have room on the slide to put the whole text of the change request, but basically it says, the limit is 90 parts per million, but there's an exception. And the exception is for operators who prove they can perform dilutions accurately and test cyanuric acid concentrations accurately above 90, then they should be allowed to go up to 180 parts per million. Again, this is kind of based on the ratio concept. So the risk doesn't increase as long as you maintain that ratio. And so why not go ahead and let people go to above 90 parts per million as long as they maintain whatever ratio is chosen by the CMAQ voters. So if your ratio is 45-to-1 and you have a 4 part per million DPD-free chlorine, which is the maximum from EPA, then that comes out to be 180 for the maximum for cyanuric acid. And the argument is that some operators should be capable of performing dilution, so why not let them go ahead and take advantage of the fact that they have that skill set and let them go above 180 as long as the ratio is maintained. The arguments against this are that the NSF listings of test kits, they all max out at 110 parts per million. So NSF, they do have a means of testing greater than 110. So if you look in the NSF 50 and it talks about testing test kits, that there's provisions for testing up to 200 parts per million of cyanuric acid using dilutions. So we don't know whether test kit companies have, tested above 100 and just didn't pass the quality criteria, or whether they just didn't test at all. All we know is that there aren't any test kits that are currently listed above 110 parts per million. And I want to point out the accuracy levels that are required in that little table on the right there. There's various levels of test kits within NSF 50. L1 are the most accurate test kits. So these are the electronic photometers, or photometers, excuse me. And so you can see plus or minus, 10 to 15% for the results that you're getting from those units. The L2 kits are plus or minus 20%, and the L3 kits are plus or minus 50% or within 1 increment. So it turns out that all of the L1 and L2 test kits currently that are listed, they are all test kits that involve using a spectrophotometer or photometer. All of the ones that don't involve using those instruments, so the drop test kits, the test strips, those are all L3. So for the cyanuric acid test kits that, cash-strapped public health inspectors might be using would probably be in the L3 category, where it's plus or minus 50% or within 1 increment. So there's certainly issues with the 180 parts per million as a limit, given that the range on those test kits could be plus or minus 50%. So if you had actually a concentration of 300 parts per million, it might appear to be 150, or it might appear to be 450. And if it appeared as 150, you might be thinking that you were okay. So even though you had 300 parts per million, that it might appear to be within that 180 part per million limit that's in this change request. Another issue with this change request is that the ORP control is not effective at high cyanuric acid levels. With high cyanuric acid, the response is levels out, and so it's really hard to control your chlorine feed when you have high cyanuric acid in the water. Another issue is that training will be needed for the health inspectors and the operators to do the dilutions. The operators certainly will have the incentive to do the dilutions because they'll give them more flexibility in their operations, but we really need to make sure that the health inspectors are trained as well so that they can do the dilutions, and that when they are inspecting a facility, then they can reliably check the cyanuric acid concentrations that are in the pool. One of the issues also with this change request, if you have 180 parts per million of cyanuric acid in the water and you need to do a diarrheal fecal accident response, that requires that you lower your cyanuric acid to 15 parts per million. So essentially you're going to be draining all of the pool in order to be able to do a diarrheal fecal accident response. This value also exceeds the World Health Organization toxicity limit of 117 parts per million, and we will be talking about that one later. And it will also increase the risk versus the current code. So this is similar to those graphs I showed you earlier, except what would happen now if we don't just let that rate, the cyanuric acid concentration, keep climbing depending on our DPD-free chlorine, but we actually limit it. So if we limit it to 180 parts per million, this is what the chart would look like. So you can see it's still an overall increase in risk compared to the current model aquatic health code, but just with that 45-to-1 ratio, but just wanted to show you how that would look. All right, so these next change requests are about testing frequency. John Kelly proposed that daily testing be done, and our committee recommended that weekly testing be done. Currently, the MAC requires testing every 2 weeks. The reason for that is that if you're using ISOs, if you're using trichlor, you're contributing 0.6 parts per million of cyanuric acid for every part per million of DPD-free chlorine that you contribute to the pool. And for dichlor, that value is 0.9. So you can see that if you're feeding, 5 parts per million of DPD-free chlorine per day, that these cyanuric acid concentrations can climb pretty quickly. So the way that the change request from our committee is written is that it's weekly testing or more as needed. So if you are feeding a lot of chlorine with high chlorine demand with the stabilized sanitizer, you might need to test more often than weekly. This next change request is basically just to include cyanuric acid and HOCl into operator training. So any operator training course needs to include what's going on with cyanuric acid and HOCl and disinfection. This next change request is about formed stool response. So currently in the Model Aquatic Health Code, Giardia is the target organism. And the CT value for Giardia, so the concentration times time needed to inactivate Giardia, is 45 parts per million minutes. So with 1 part per million of free chlorine, you would kill the Giardia within 45 minutes. And the current Model Aquatic Health Code procedure is to treat for 2 parts per million for 25 minutes with no cyanuric acid, and then just to double the time if you have cyanuric acid present, so 2 parts per million for 50 minutes. But what if we were to say, okay, well, let's take what we know about HOCl and look at what would happen then to these Giardia target kill times if we look at HOCl instead of DPD-free chlorine. So this is a chart I showed you earlier. If we have a CT value of 45, we have cyanuric acid increasing, what happens to our HOCl concentration and what happens to our treatment times. So if we have no cyanuric acid, 1 part per million of free chlorine, our HOCl is about 0.5 and we're killing it in 45 minutes. Now with 10 parts per million of cyanuric acid added in, it's going to take about 10 times longer. With 20 parts per million of cyanuric acid, it's going to take about 20 times longer. So how can we write that into code language so that we can make sure that we're treating the form stool to kill Giardia? So the best way to describe this change request is just to take you through an example. So let's take an example of a pool that has 50 parts per million of cyanuric acid in it. So if we have 50 parts per million cyanuric acid, and let's say we want to treat it with 5 parts per million of DPD-free chlorine. So that would be a 50-to-5 ratio, or 10-to-1. So we would look over at the table over on the right-hand side and see for a 10-to-1 ratio, that means that we would have to treat the pool for 9 hours. So if we had 50 parts per million in our pool, we want to treat with 5 parts per million of DPD-free chlorine, it's going to take 9 hours to do it. So we might say, okay, well, that's too long. Let's raise our chlorine and see how much, how we can shorten that time. So let's double our chlorine. So with 50 parts per million of cyanuric acid, let's add in 10 parts per million of free chlorine. So that's now a 5-to-1 ratio. We look at the table over on the right, 5-to-1 ratio. That means we're going to have to treat the pool for 4 hours. So you can see these values are much, much longer than what's currently in the Model Aquatic Health Code. But if we want to treat Giardia, and if Giardia is our target, and we want to make sure that we have enough HOCl in the water to kill Giardia, then that's where the math comes out of what we would need to treat. So that logic and the technical logic is there, but there are arguments against this. One is it's just difficult to achieve. It's going to be really hard to get people to do fecal accident response with these longer times and higher dosages. So the comments that have been submitted were, okay, well, can we look at other options? Can we allow secondary disinfection? Can we change the goal? Instead of using Giardia as the organism, should we be looking at a different organism since we don't have a lot of outbreaks from Giardia? Would we want to just look at localized treatment in the area where the fecal accident was found? Of course, we don't know how it moved through the pool before it was actually found, but could we do a localized treatment? Essentially, when the TRC discussed this change request, CDC told us that they are considering it and they will get back to us. So we don't have any changes to this change request from CDC, but hopefully that will be coming from them soon, so that we can, now that we know what we know about cyanuric acid and HOCl concentrations, what do we need to do about this fecal accident response? Our committee is also looking at that and, what is the risk from a fecal accident so that we can inform any decisions that are made. All right, next I'd like to talk about the group of imminent health hazards. So in the back of the MAC, there's a section about what are the things that are really critical, where if these are not in place, the facility needs to either immediately correct it or close the facility. And so within that, there's several different change requests that have been proposed. And just so you know what's currently in there, if you look at the bottom of the slide there, it says current MAC IHH, failure to provide the minimum disinfectant residuals listed in various sections of this code. So that means that currently, if you have less than 1 part per million of free chlorine with no cyanuric acid or 2 parts per million with cyanuric acid, that if you don't have that minimum disinfectant, then that means that you would need to close or correct it immediately. That also means that if any of the change requests that I've just talked about with the ratio or any of the others are implemented, then because this references various sections of this code, if a 15-to-1 ratio were accepted for operational, and if no change is made to the imminent health hazards in the back of the MAC, then that means that 15-to-1 ratio then would be a reason for immediate correction or closure. So it's important to know, how the different parts of the MAC interact with each other, and to know, like decisions that you might make for operational parameters can also affect this section of the Model Aquatic Health Code. So let's talk about the individual change request. One is just to take the operational limit that's currently 90 parts per million for cyanuric acid and make that a reason for closure. So that's a very simple to explain change request. We know that there's insufficient disinfection when you have high cyanuric acid levels because you have very low HOCl concentrations. And we know that the current MAC limit is 90 parts per million of cyanuric acid. And so that HOCl level for closure then from this change request would essentially be 0.02 parts per million. HOCl would be a reason for closure. The arguments against this are, for all of these, it's disagreement over what constitutes an imminent health hazard. At what point do you actually have to close the pool? This next change request has been through some changes recently, and it would recommend closure for a ratio greater than 45-to-1, and then also putting an absolute maximum of cyanuric acid at 300 parts per million. It also specifies that 1 part per million DPD-free chlorine would be the minimum for all pools, with or without cyanuric acid being present. So the arguments in favor of this are that the HOCl level for closure would be 0.02 parts per million, as we talked about before. And that's the current HOCl concentration that's allowed currently in the Model Aquatic Health Code. It's consistent with the current MAC practice of using disinfection operational limits for closure, so that 0.02 parts per million. And that 300 part per million cyanuric acid limit is taken from an NSF International publication that was recently submitted. And they looked at the toxicity of cyanuric acid and looked at the EPA swim model for assumptions of, how much people swallow when they are swimming, and, how long do they swim? And so what does that mean that the concentration of pools should be limited? And they calculated that the limit for cyanuric acid for toxicity should be at 305 parts per million. This change request is also consistent with the 2 part per million free chlorine minimum. I'm sorry. Just wanted to point out that this is replacing the 2 part per million free chlorine minimum with cyanuric acid with that 45-to-1 ratio, rather than saying that you have to have 2 parts per million when cyanuric acid is present. And the question about, going up higher than, 100 parts per million, operators and inspectors should be able to perform dilutions to measure greater than 100 parts per million of cyanuric acid accurately. It will take some training, though, in order for people to be able to do that accurately. Arguments against this change request: again, disagreement of what constitutes an imminent health hazard, and does, that 45-to-1 ratio, does that represent an imminent health hazard or not? Or should a different ratio be chosen? There's also questions about which toxicity limit to use. NSF has calculated 305 parts per million. The World Health Organization, which I mentioned earlier, has a limit of 117 parts per million for their toxicity limit. So there's differences in opinion of which is the best toxicity limit to use. Because this is raising the limit when you have cyanuric acid present, instead of being 1 part per million, or instead of being 2 parts per million with cyanuric acid present, it's now 1 part per million. That is increasing the risk to some extent. So there's an increase in risk with this change request. And then, of course, there's testing, concerns over testing of high cyanuric acid concentrations, and the things we talked about earlier with test kits having a plus or minus error on them. And all of the test kits are maxed out at 110 parts per million that are listed currently on NSF website. All right, this next change request is for a different ratio of 150-to-1 and with the 300 part per million cyanuric acid absolute limit. And again, saying that you can have 1 part per million minimum free chlorine for all pools, whether or not cyanuric acid is present. The arguments in favor of this, again, that cyanuric acid limit came from the NSF calculation. As far as that 151 ratio, if you look at the change request justification, it states that this ratio is 1.7 times the 45-to-1 risk. Now, this 1.7 number is calculated using the author's assumptions, and the author says that it's 3.2 times the risk for the 45-to-1 if you use the defaults. Personally, when I did the calculation, I got a different number, but these are the numbers that I got from the change request. So essentially, with the 150-to-1 ratio, that would mean that the HSCl level for closure would be 0.002 parts per million. So we talked about earlier about how with 2 parts per million of free chlorine and 90 parts per million of cyanuric acid, that your HSCl concentration is 0.02. So this 0.002 value is a tenth of the minimum HSCl that's currently allowed in the Model Aquatic Health Code. The risk, though, is not 10 times more than that 45-to-1. And one of the reasons for this is because when your disinfection is so slow due to all that cyanuric acid in the water, that other mechanisms like filtration and die-off of your organisms have more influence. So that if you do the calculations with the risk model, you won't see that the risk increases 10 times, even though your disinfectant concentration is a tenth of what it was. Just because, filtration makes a difference when your disinfection times are so long. One of the other arguments about this ratio is that looking at Pseudomonas bacteria and calculating how quickly they can reproduce, and if you want to be able to kill them as quickly as they are reproducing, then this 150-to-1 ratio works. However, even if you're balancing out that rate of kill versus growth, you can still have a very stable high concentration of pathogen present in the water. Another argument about this change request is the Pinellas County data indicates that 73% of the heterotrophic plate count disinfection failures would have been avoided with this ratio. Of course, Pinellas data can be parsed a lot of different ways, but essentially the data also indicates that you could prevent greater than 73% of these failures if you had a lower ratio. The outbreak data indicates that 1 part per million of free chlorine is enough. Of course, cyanuric acid is not typically measured in outbreaks, which we've talked about already. And another argument about in favor of this change request is that currently the it's not an argument in favor, but just to point out that that 2 part per million free chlorine minimum is replaced with the 150 to 1 ratio. I think I've discussed most of the arguments against this one already as I was discussing the ones for it. Disagreements over an imminent health hazard and what is actually an imminent health hazard and what should a pool be closed for. There's disagreements over which toxicity limit to use, the NSF value or the World Health Organization value. And of course, 150 to 1 would increase the risk currently than what's currently in the Model Aquatic Health Code. All right, this next change request is a new one, another one from John Kelly after listening to all the arguments during the CGMAT conference. And he is suggesting closure with the World Health Organization toxicity limit of 117 parts per million and keeping the limit of 2 parts per million of DPD-free chlorine when you have cyanuric acid present. So the arguments in favor are that this is evolution, not revolution. Let's keep those limits of 1 part per million free chlorine for pools without cyanuric acid, 2 parts per million of free chlorine with cyanuric acid, and keep it the way it was. And so this is just spelling out the requirements that are already reasons for closure, but spelling it out in the section that's about the MAC. And sorry, the section about closure. The advantage of this change request is that the other closure change requests lower that limit, right? Where any pools with cyanuric acid could have as low as 1 part per million of free chlorine. And then the argument in favor again is the World Health Organization has this toxicity limit rather than the NSF organization. Arguments against it, again, disagreement of what is exactly an imminent health hazard, question whose toxicity limit should you use, and concerns over testing, because 117 is a really precise value, and as we've seen, the maximum NSF listing is 110 parts per million, and the L1 test accuracy is plus or minus 50%. So it can be very difficult to measure such a precise number. And of course, then there's concern over the cost of compliance. So even though, for decades, in the MAC and the other standards, state codes, APSB standards, cyanuric acid has been limited to 100 parts per million for a long time. And so, it shouldn't be any surprise that people should limit it, but to actually have to enforce 117 parts per million of cyanuric acid would cost more for compliance. All right, so yeah, just wanted to circle back around with some tools for you so that you could judge for yourself which number is the right number to use, NSF or the World Health Organization. The full NSF document that spells out exactly how they came up with their 305 parts per million toxicity limit for cyanuric acid, it can be found as an attachment in change request 6631-5. The World Health Organization document, there's a link there to it. And then if you look on pages 84, 87 through 88 of the PDF and the supporting references, then that's where all the information is regarding that toxicity limit. The argument about which of these is the right number hinges on a number of different things, but primarily on the exposure estimates. How much time are people spending in the water and how much water are they ingesting? So you can use the EPA swim model to kind of play around with these numbers. There's a link there to show you where the swim model is located. There's an Excel spreadsheet that you can pull down, and then you can enter whatever numbers you want and see what happens then to the exposure values, and then see what happens to whatever maximum concentration would be allowed. The justification section for CR 6631-0003 has some additional information on sources of data for how much water do people drink? How much time do they spend in the water? So if you're trying to figure out, well, what value should you put in there? There are people who have looked into this and published data on it, and so some of those references can be found in the justification for that particular change request. So there's a number of different things that are out there to kind of aid you in inputting data and trying to figure out which makes the most sense, and just wanted to provide you with those resources. All right, so overall, would like to share with you what my recommendation would be. I think that we need to define DPD-free chlorine to make sure that we're all speaking the same language, and to make sure that the Model Aquatic Health Code is consistent about what's being required. Next, as far as the actual free chlorine concentration and what would be required, I'm personally a fan of the 15-to-1 ratio. That's a change request that I submitted. I really don't think that we need to have our chlorine be less effective than 1 part per million of monochloramine. So I think the 15-to-1 ratio would be the best for public health. But I think that that table that's in the change request that John Kelly just submitted comes really close to that 15-to-1 ratio. And so I think either one of those change requests would be fine. The change request that John Kelly submitted regarding the 90 part per million limit and keeping that, but draining overnight down to 75 if you exceed it, I think is a really good idea to help public health inspectors as they're inspecting facilities to get action and to make sure that if it's over 90 that something is done. I think that weekly testing is sufficient, and particularly with the way that that change request is written, that if you are using a lot of trichlor, that you may need to test more often than weekly. I think that operator training courses need to include training on cyanuric acid and HOCl concentrations and the effect on disinfection. The form stool remediation, I think it's a good idea, but CDC needs to get back to us on what they think would be reasonable. And I think they're going to be waiting on our committee to do some risk calculations to kind of get a feel for, what kind of risk would be involved with making changes to the remediation protocol. And finally, for closure, the change request that John Kelly recently submitted, 117 parts per million for the toxicity limit, and then keeping the 1 part per million free chlorine for pools without cyanuric acid and 2 parts per million of free chlorine with cyanuric acid. So those are my personal recommendations. And as you can go into the CMAQ website and see what the technical review committee is recommending as well for all the different change requests. So finally, just want to conclude that we know HOCl is the primary disinfectant. We know that cyanuric acid lowers HOCl concentration, so it takes longer to kill pathogens. Longer kill times are going to result in greater risk of illness. We can't measure HOCl in pool test kits, but we can measure DPD-free chlorine and cyanuric acid to estimate our HOCl concentration. So we can all agree up to this point, the science is very clear. What we don't know how much HOCl is enough. 0.32 parts per million, which would be enough to be registered as a EPA sanitizer. And is it 0.026 parts per million, which would be a 15-to-1 ratio, or 0.0086 parts per million, which would be a 45-to-1 ratio? How much cyanuric acid is too much? Which toxicity limit should we use? 117 from the World Health Organization, or 300 parts per million from NSF? Or should we limit it based on more practical considerations, such as what would be the ORP operational limit? Just looked at a few ORP controllers out there that had their manuals on the web, and saw that there was one manufacturer that recommended a maximum of 100 parts per million of cyanuric acid, another one that recommended 30 to 50 parts per million of cyanuric acid. So would we want to limit it based on ORP? Of course, somebody could use ampere metric. Of course, those units are thousands of dollars rather than hundreds of dollars to use ampere metric. But hopefully, new technology such as membrane probes and things like that will have sufficient accuracy as well as reliability in the presence of cyanuric acid and be cheaper, I hope. And then there's the test kit limitations. Do we limit it to what you can achieve without dilution, or can you do dilution? And of course, anytime you do dilutions, you introduce some error in the values when you do that. Or do we want to base it on, a ratio, or base it on just absolute HOCl limits or tables? There's all kinds of ways to limit it, and what is the best way? Hopefully, we can all decide and with our votes. And of course, then what constitutes an imminent health hazard? At what point do you have to get everybody out of the water to avoid disease transmission? And then practical aspects of training. How many operators and inspectors can be proficient with ratios? How many can be proficient with dilutions? So these are all unanswered questions, and so there's no clear-cut way to sort through all these change requests and try to figure out what is best, but would certainly like to wish you the best and to help support you in that effort. In this presentation, there's various references that you can pull down and look at the data. In particular, you can see in red there, the paper was originally published, and if you pull down the supplemental information, you can pull up a copy of the spreadsheet that has the model in it, so you can do your own risk calculations. That model has been updated to include things like diurnal variation and the new EPA fecal introduction rates. And so there's a website there that you can pull up the most recent model that Richard Falk has provided for us, so that you can do those other calculations with diurnal variation and the other things that we talked about today. And then there's more references here. And finally, I would like to thank you for your attention through this very long presentation. I hope it's useful for you as you sort through all the change requests and all the data and all the issues. Thank you for your attention to this issue. I think it's really critical for public health. And I'd just like to thank you for voting to help improve the MAC. Stay safe.